So yeah, this talk is called One GPU to Rule Them All. And I'm just going to cut straight to three numbers that are important here. And that is 13 servers, 1% utilization, and $3,000 a month in cloud expenditure. And I want you to hold those three numbers in your head because they're important. And by the end of this talk, they're going to be summarized into one number. And these are the numbers of our pipeline. It was an image classification system that could barely keep up with the workload. So here's the story. We had an image classification system, and it's maybe the kind of pipeline that nowadays a lot of people are running, a lot of teams are running. And we wanted the obvious way, right? So we were asked that it can serve multiple models. And these models, of course, needed to be load balanced at the beginning, and they need to have their own web server. They need to react. They had their own compute CPU instances. They were always on because we didn't want to to cold start. The system worked. Nobody complained. And I think that's a gap, right? Sometimes when nobody complains, we don't look at stuff that is broken. And this continued happening for some time until one day, somebody just pulled up an utilization chart on cloud and was like, what are these servers actually doing? That's a simple question. And the answer was almost nothing. As you can see, it was 1% utilization. And that's the central topic of this talk. It's when should you ask yourself these kind of questions? And if you're an engineer, do you have to think about these kind of questions? Because our job is not only about technology. And when you imagine about having to deliver, for example, handful of letters, right? Let's say you have that task, you have to deliver those letters. What would be your thought process to solve that problem? Would you go straight ahead and hire a fleet of trucks to get it done? Of course not, because to optimize a problem, you need to understand the scale of your operation. And you don't solve the problem of handing out 5 letters with trucks. So that's what was happening here. We had 13 instances running full time. And I know that some of you are thinking, maybe we're not that inefficient at the place where we're working. It's hard to miss this in our stack, but I'd encourage you to check it out. I'd encourage you to go back to your own utilization charts, your own Kubernetes clusters, and check out, because the secret is that when you're doing inference with a CPU, your utilization lies to you. And I'm going to explain a little bit more about, but your cluster could be reporting utilization that is much higher than this. But when you filter out all the other stuff that the CPU is doing, then you'll find out that something like this is what's actually happening. And you're just paying for the other amount of compute without getting actual value from it. Remember that these kind of processes that are running, even if it's a LLM, even if it's a vision model, they're running on a regular system and they have overhead, right? They have critical systems. They're running a web server. They're running negotiating traffic, doing garbage collection. And this is where we could miss out on these kind of optimizations. So that's how our charts could be looking. But remember, they could be lying to us. And what would be the decision framework that this talk is about? And I want to give you so that you could decide when to migrate your workload from CPU to GPU. And why would we land in this problem? The reason why we landed this problem is because there's startups spinning up every day. And a startup initially has an idea, but could probably have not found product market fit. And it probably doesn't have the amount of users, right? So the obvious way to build something could be, let's do it the cheapest way. And the cheapest way could be just putting on a CPU, right? But is that true? And let's start with the 3 questions that you're going to do to yourself and to your team to diagnose that. same problem. The first question is, what is your actual inference utilization? And to uncover this, you will need to think about the other things that are happening in your other things that are happening in your system, and really filter out your actual modern utilization, not your overall utilization, not what your pod is reporting, what is actually running the inference. That is the first question of the framework. What is the second one? The second one is, what is your cost per inference? And your cost per inference is not just dividing or just taking the amount of time it takes to do an inference and trying to figure out the cost. Is what is your total cost per inference? So what is your total infrastructure for that inference pipeline costing you in the cloud, and dividing it by the amount of monthly predictions that you're supposed to be doing or that you're doing, right? And we did this math. And in our case, the number it wasn't bad. It was embarrassing. Like, why hadn't we looked at this number yet? And the third question is, can your model actually exploit GPU optimizations? Not all the models are built the same, right? We know that in the perfect world, all the models can be compiled to C code, or can be ONNX, or can be in a more optimized, quantized model, but not all models can do this. And so you need to identify, can my model benefit from batchable inference? Can my model be quantized? Is it like a image classification pipeline, which for that, the answer is almost universally yes. But for some LLMs, for example, that can be compiled into TensorRT VLLMs, then you can also achieve this goal. And so if you ask yourself these three questions and the answer is yes, you should start. You have a huge opportunity to optimize. And I want to show you the before and after of our architecture, explain a little bit more about our thought process, about the things that we were aiming to resolve, and how to do some trade-offs so that you can learn how to apply this in the real world. So here's the before and after. Before, we had kind of like this load balancer that would pick a model, and this routing would go to a specific server and would serve the inference and respond, right? But one of the big faults here, as you can see, is that we're running 13 deploys, and in this model, we're running 30 pipelines. So there are 13 things that can go wrong, right? Now, what was the after? You can see here that in the after, there is a lot less moving pieces. Like, there is a KServe ingress, and there is a GPU that is loading all the models that we need. So now, this is one deploy, one pipeline, one failure point. And that is huge for operational and for cost efficiencies. What was the stack that we used to kind of migrate from CPU to GPU? And why did we choose this stack? This stack is great for any type of machine learning model. So, of course, I'm presenting here one of our personal projects that was more computer vision based. But remember that KServe, for example, coming from KServe or Kubeflow, if you know, is an MLOps for all types of machine models, and it's a controller that sits on top of Kubernetes. Triton, it's an inference service. It's an inference server image created by NVIDIA that allows you to get some free tool for running inference on your servers. And Google Kubernetes Engine, the platform that could be any cloud provider. And we were using NVIDIA L4 and T4, which were just the cheapest. So let's go a deep dive into each of these things to understand kind of some of the trade-offs and the advantages that we found as we were switching to this specifically. So why did we choose Triton? Triton allowed us to kind of get a few things for free. The first thing was like multi-model serve. So as you saw, one of the problems that we had is that we were serving for 13 models. We're trying to cater to a lot of models at the same time. And this multi-model serving is just consolidation. Instead of having 13 different deployments, the Triton server instance is able to share GPU, share CUDA context, using the overhead of all of that into a single GPU, right? So imagine having an LLM, a classification model, clustering model, or any other subset of smaller models all running in the same GPU. And the CPU component is Triton doing the multi-model management of that memory. The second one was dynamic batching, and we talked about this a little bit before, which is one of the criteria before you decide to switch. And Triton solves that problem for you. You don't have to kind of code this batching. Triton solves it for you, and it allows you to transform a bunch of requests into a single GPU pass. And this makes it a lot cheaper to run the inference, because for the same wall clock time, you're doing n amount of operation, meaning for us, it was one image, take the same amount of time as 10 or 12 images if they're batched up to the same GPU pass, which was aligned also to the third criteria, which is quantization. So Triton has native backends for quantized models and for compile to C models, right? So if your model is able to be compiled or to be quantized, Triton has native backends for these kind of things. We haven't reached this goal in our current implementation, but it's something that we're eyeing for the future, and something that you should take into account, because it could provide up to 2 to 3 times even more throughput. How about the actual cloud compute? What was the advantages of switching from CPU to GPU using this kind of infrastructure? Well, GPU is very expensive. And if you don't prioritize the compute that's going to the GPU, you might be wasting GPU for cheap compute, right? What this architecture kind of solves for us is that Kubernetes and Triton are putting the difficult task in the most expensive part of the infrastructure, which is GPU, right? So this is architected for utilization. You want the highest ROI of your inference being gone to what's costing you more, which is the GPU, and what's arbitrary in your code to be run the cheapest way possible by a CPU, not the other way around. So this architecture helped us solve that. I want to also go through some of the other alternatives that we consider when we're implementing this, so that if you're ever considering switching from CPU compute to GPU compute, you can also look at other alternatives that could serve the purpose. And all of these are trade-offs that will help you and that are according to your own infrastructure or own decisions. And the first one was GPU time sharing. So we were already running a bunch of servers, right? And what happens if you could just plug a GPU and have these servers talk to the GPU? Then this GPU would just serve these models, and we would have to kind of architect the way or engineer the way for these 13 models to share this GPU. Just by describing it, you know this is hard, right? Being able to manage the memory of a GPU by many other servers is a difficult orchestration task. And we didn't have to do that because Triton already offered multi-model server serving on the same GPU. So it was doing the hard lifting for us. We also consider bringing in the big guns. So if you're acquainted with cloud infrastructure, you know that A100 and A100 GPUs could have 80 to 160 gigabytes of memory. And you're thinking, well, this is great. This is going to be fast. But when we started doing the actual numbers, we decided, or we saw that it was actually an overkill. We wouldn't get much benefit beyond a specific amount of compute. And we wouldn't get a return in terms of value from just putting in more and more compute into it. how did we look at this trade-off without spending a bunch of money, right? So we distributed the task in the team to do what was just a cost analysis. Let's try to do running of a specific test, scope test of thousands of images or thousands of units of work of your runtime in these specific GPUs. What was the outcome? What was the time? How much did it cost? How long did it run? And by answering all these questions, we were able to not make the expensive mistake of just putting bigger guns on our specific problem. And the last trade-off that we did was, why would we choose a Kubernetes and manage our own infrastructure rather than choosing a managed service like Vertex AI or like SageMaker? And this was basically reference to the trade-offs of this system. So we knew that our pipeline needed specific and precise control over a specific criteria that was hard to configure or harder to configure in these managed inference platforms. Your trade-offs might be different, but we want to share that with you because every architecture is just a set of trade-offs, and you will have to make your own. Of course, not everything had to be good. Every time that we make such a change of runtime, we might think that we've thought about everything and we did all the trade-offs, but here are some things that we found when we actually started implementing. The first thing is that GPU cold starts are very different from CPU cold starts. And as you start working with GPUs, you will learn CPU might take 30 seconds to cold start. That's annoying, but it's not a deal breaker. But GPUs are very different because when it's being managed by Kubernetes, the node has to provision. For the node to provision, the resources in the cloud need to be available. And everybody in San Francisco is trying to tap into the same pool of availability. And that cannot be instantaneous. There's also the time to download the container image into Kubernetes runtime. And then the model waits to download into the CUDA context into the GPU. When you start adding all these things up, you will note that to start a pod from zero, you will find 3 to 8 minutes, sometimes up to 15 minutes. GPU is not available for it to start. How did we manage to work around this hurdle? So there are 4 layers that you can implement that we haven't implemented all of them, sadly. We're working towards that goal. But there are 4 things that you can implement to kind of move from 8 minutes to 30 seconds or no cold starts at all. And it all starts with using your tools in the cloud, correct? So Google Kubernetes Engine, when you pair it with the artifact registry on the same platform, it allows you to stream the image by layers. So you don't have to download the whole image complete every time there's an update, and you only transfer the layers that change. And so that reduces the image pool from minutes to 30 seconds. But if you don't configure it, you're always downloading the total image completely every time you cold start. So make sure to configure that. There's also alternatives for Kubernetes, which is plugging in some SSD onto the Kubernetes cluster and taking the images that are always being downloaded into the CPU closer to that. Also configure Triton to do a model warm-up, and Triton can send dummy requests to the GPU before actually serving the requests coming from outside to get the CUDA context warm up, so that the first request just serves the same as 1,000 requests. And you can also ask your business, when do we actually need the compute? Do we need the compute 24/7? Are we actually serving 24/7 clients? When can we turn this off? Because if we keep it running all the time, we're going to spend all the time. But are there dead hours in our workflows that we can configure into our Kubernetes to just pin down everything when it's not in use? This is some configuration that we made. Don't take this for actual code. It's just a representation of asking the business, what were the actual times that our customers were using the platform? Just configuring our Arcada to turn off stuff when we're not using it. The second lesson is that GPU and CPU are very different to monitor. So CPU monitoring has been already standardized across the cloud. And some of this happens without you even having to configure anything. But for GPU monitoring, it's very different because the GPU load not actually tell you anything about how the GPU is being taxed. You want to know what the queue back, how long the queue is waiting in the GPU, how long it's actually taking to compute. Remember, this is parallelized workloads. So you want to know how each parallel thread is taking compute. And by implementing specific monitoring metrics, the ones that Triton already gives you out of the box, it would allow you to monitor the GPU different way from CPU. And of course, the hardest part is not the code. How do you pitch this to a company that where all the executives believe that CPU is actually the cheapest alternative? Because it's very different to look at the price tag on a CPU on the cloud, where it's costing you 0.00 cents an hour, and then look at the GPU and says it's costing $150 an hour, and convince the finance person that the GPU is actually cheaper. I'm going to show you the numbers because they're really amazing. So when you implement batching, when you implement optimized runtime, when you implement quantitization, you can reduce all of that deployment, which is costing around $36,000 a year, to an 80% reduction. And we're talking about a GPU that is orders of magnitude more costly per hour. But what's happening? Remember that when you implement all these things, you're actually making your system 22 to up to 105 times more optimized. It's optimized for utilization. It's not running. It doesn't have to be running. Beyond the cost, you will see that when you simplify your workload, you also unlock operational efficiency. When you choose the correct technologies, you unlock new capabilities without having to code a single line of code. So I want you to take 3 things home. It would be nice that you go tonight and you check your inference utilization, but you thoroughly think if the charts that you're reading are actually telling you your utilization of inference. I also want you to see that GPU tax is a myth. Just because the cloud prices are crazy, it doesn't mean they're actually more expensive. You can save 80 to 90% of your cost by switching to GPU and doing it the optimized way. And faster doesn't have to be more expensive. It just means architecting the trade-offs properly. Guys, that was one GPU to rule them out. Thank you for your attention.